Okay. Let's say we have and let's let B be, well, let's do this first. Solve the homogeneous system. A times X equals the zero vector. First of all, let me ask you a question. Before we even do all the work, do we know there's going to be at least one solution to that matrix equation? I see you shaking your head yes, you're absolutely right. What solution, before you even do anything, do you know is absolutely going to be a solution? What solution is always a solution to a homogeneous equation?
Zero.
Yeah, zero. X equals 0 will definitely be a solution. So we know a priori, we know in advance that X equals 0, 0, 0, 0. In other words, X1 equals 0, X2 equals 0, X3 equals 0, X4 equals 0 will definitely be a solution, because if I take A and multiply it by that zero vector, I'm going to get the zero vector. This zero vector, by the way, is 0, 0, 0. The thing on the right-hand side of the equation has the same number of entries as the matrix has rows. The X has the same number of entries as the matrix has columns. So if I take A and multiply it by this, I will definitely get 0. That's definitely going to happen. Let me ask you a second question. Do we know for sure that there's going to be infinitely many solutions? I see Jalen's head going up and down, and he's absolutely right. How did you know that, Jalen?
I don't know. I just think it's going to be infinite.
Your guts are saying yes, and your guts are right. But we know in advance we're going to have infinitely many solutions. What can you tell me about the number? What can you tell me about free variables? Can you talk to me about free variables?
You mean me specifically or anybody?
Anybody is fine.
We know that there's at least one free.
There's going to be at least one
variable.
free variable, right? Because the original matrix has 3 rows and 4 columns. We can't have more pivot positions than we have either rows or columns. So in this case, we can't have more than 3 pivot positions. So the original matrix has at least one column without a pivot position in it. So it has at least one free variable, which definitely means we're going to have a free variable. So we have, not only do we have this solution, but we have infinitely many solutions. So we know we will have at least one free variable. So we will have infinitely many solutions. So not only one, but infinitely many. By the way, I've noticed that a lot of you are watching the videos after class, the recordings of the class. Are those helping? Does it help to have me stop and say it over again? You can pause me anytime you want. You probably wish you had that power in class sometimes when we're here in person. But this time you definitely do. Okay, great. I'll definitely keep posting them, and you can keep watching them if it helps. Okay, so let's go ahead and we could take this system, A times x equals 0. So in other words, A was 2, 4, 2, 2, 1, 3, 3, 3, 1, 1, 4, 6. And x was x1, x2, x3, x4 equals 0, 0, 0. And we could write this in a variety of different forms. We could write it as a vector equation. We could write it as a system of linear equations. We could write this as 2x1 plus 4x2 plus 2x3 plus 2x2 equals 0, and so on. But the easiest thing to do to actually do computations in, because it's the least writing, is write it as an augmented system. So let's go ahead and write this as an augmented matrix. So 2, 4, 2, 2, vertical bar, 0. 1, 3, 3, 3, 0. 1, 1, 4, 6, 0. And let's go ahead and row reduce. Let's put this into reduced echelon form. So the first thing I need to do is get a 1 up here. There's a variety of ways I could do that. I could switch rows, 1 and 2 or 1 and 3. I'm just going to take the first row and multiply it by a half. So 1/2 times the first row. So what? 1, 2, 1, 1, vertical bar, 0, 1, 3, 3, 3, and 1, 1, 4, 6. Now I have a 1 in the upper left-hand corner. I have a 1 in this pivot position. I know this is a pivot position now. I have to get zeros below it. I'm going to get zeros here and here at the same time. So 1, 2, 1, 1, 0. I'm going to take row 2 and subtract off row 1 to get, let's see, 0, 1, 2, 2, 0. And I'll take row 3 and subtract off row 1. So 0, -1, 3, 5, 0. So here's one pivot position. I can already see another pivot position, and I have a 1 there already. So let's get a 1, let's get a 0 below that. So I'll leave row 1 alone for now. 1, 2, 1, 1. I'll leave row 2 alone for the moment. 0, 1, 2, 2. And I will take row 3 and add 1 times row 2. So I end up with 0, 0, 5, 7. Ugh. Okay, my poor choice of numbers, I can see I'm going to end up with kind of ugly fractions sooner or later. I guess I'll just live with that. Okay, so we see a pivot position here. We see a pivot position here. We're going to have another pivot position right here. Let's get a 1 there. The best way to do that is to take the third row and multiply by a fifth. So I'll leave the first 2 rows the same for now. 1, 2, 1, 1. 0, 1, 2, 2. And we'll take 1/5 times row 3. So we have 0, 0, 1, 7/5. I guess that's not too bad. 0. If you don't like 7/5, if you want to call that 1.4, that's fine. And now I have to go ahead and get zeros above my pivot positions. Excuse me. Once again, this classroom.
Bless you.
Thank you. This classroom is so full of chalk dust right now. It's amazing that you can't see clouds. So when we get zeros below the pivot positions, we move from left to right. When we get zeros above the pivot positions, we move from right to left. So we'll get zeros here and here first, and then we'll get zeros, we'll get a 0 right there. So let me get a 0 here and here. I'll do this in one step. I have to move this over a little bit to have room. So I'll leave the third row alone for the moment. 0, 0, 1, 7/5. But I want to make that a 0. So I'll take row 2 and subtract off 2 times row 3. So notice whenever I'm working in the second row, if I'm going to use this replacement thing, that's got to be the second row first. And whenever I'm working in the third row, that's got to be the third row first, and so on. So you always take the row you're in and add or subtract a multiple of another row if you're using this replacement technique. Okay, so let's see. Row 2 minus 2 times row 3. So 0 minus 2 times 0 is 0. 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0, which was the point. And 2 minus 2 times 7/5 is, let's see, 10/5 minus 14/5 is minus 4/5. And again, if you don't like fractions as much as I do, feel free to go ahead and use decimals. You can write that as minus 0.8. And let's get the first row. Let's get a 0 there at the same time. So that'll be row 1 minus row 3. So 1 minus 2 times 0 is 1. 2 minus 2 times 0 is 2. 1, oh, sorry, not 2 times. I'm just doing 1 time this time. 2 minus 0 is 2. 1 minus 1 is 0. And 5/5 minus 7/5 is negative 2/5. So now we have zeros almost everywhere that we need. But we have zeros below all the positions and above except for right there, so we have to get rid of that too. So let's see, I will take row 1 and subtract off 2 times row 2. So that gives me 1, 0, 0. So minus 2, minus 2/5. Let's see, plus 8/5 is 6/5, I guess. And then we have 0, 1, 0, minus 4/5. And we have 0, 0, 0, 0, 0, 1, 7/5. I really wish I had more board space. So let's go ahead and write out our answer now. This says x1 plus 6/5 x4 is equal to 0. This says x2 minus 4/5 x4 is equal to 0. This says x3 plus 7/5 of x4 is equal to 0. And x4 is free, of course. So if we write out the final answer, we have, I'm going to write it over here. x1, well, I won't say the final answer. I'll just write, I'll say x1 is x1 minus 6/5 x4. Sorry, x1 equals minus 6/5 x4. And x2 equals 4/5 x4. x3 equals minus 7/5 x4. And x4 is free. Now, last time we wrote this parametrically. We assigned to each of our free variables a letter. This time we only have one free variable. We only need one letter. Let's let x4 equal, what letter did I use last time? R, doesn't matter, R, S, T. Those are typical letters to use. So I have x1 equals minus 6/5 R. x2 equals 4/5 R. x3 equals minus 7/5 R. And x4, of course, equals R. And I can write this in vector form. I've run out of room over there, but I can write this in vector form as x1, x2, x3, x4 equals minus 6/5 r, 4/5 r, minus 7/5 r, and r, which is really, I can factor out, I can pull up the r, that's really equal to r times minus 6/5, 4/5, minus 7/5, 1. And from that, you can see that the solutions, all the solutions, are on a straight line parallel to the vector minus 6/5, 4/5, 7/5, 1. That's a vector in R4. So we have a straight line going through R4, and that's where all the solutions are. Is that good? So I suppose that's the nicest way of writing the solution. So it's a straight line through the origin, because it includes the, if r equals 0, I have 0 times this, which is the 0 vector. We already knew that was a solution. If r equals 1, I have minus 6/5, 4/5, 7/5, minus 7/5, 1. If r equals 2, I have twice that. If r equals minus 5, I have minus 5 of that. Let's keep this a, but let's solve ax equals b, where b is the vector, instead of 0 this time, the last time I solved ax equals 0, let me give you a non-zero vector. How about, let's say, 2, 3, 2. Without doing the computations, do we know in advance? Can we tell in advance? If the non-homogeneous equation, a times x equals b, has at least one solution. This is based on your notes from last time, based on the lecture from last time. Does it have at least one solution? And how do you know? Oh, I see some tentative head movements in the correct direction. Searching your notes. Which is good. Let me give you a clue. I kept the same matrix A here. I have a pivot position in every row. Do we know that we're going to have a solution?
Yes.
Yes, we absolutely are going to have a solution. We have a pivot position in every row. We know that the columns of the original matrix span all of R3. So these four vectors don't all lie in the same line. They don't all lie in the same plane. They span all of R3. You can get to any vector in R3 by taking linear combinations of those. And what that means, if you take a look at that theorem with the 4 parts last time, that all 4 of these things were equivalent, we know that no matter what vector we put over here, we are going to have a solution. If you have a pivot position in every row, no matter what vector you put to the right, you're definitely going to have a solution. If you don't have a pivot position in every row, for some vectors you'll have a solution, for others you won't. But if you have a pivot position in every row, so the answer is yes. Pivot position in every row. If we had a pivot position in every column, what would that tell us? We don't in this case, but if we had a pivot position in every column, what would that tell you? About free variables. Let's start with that.
There's no free variables.
Right. If there's a pivot position in every column, there's only free variables in columns with no pivot position. So if there's a pivot position in every column, that tells you that there are no free variables. If there are no free variables, could you have more than one solution? Right, you can't. If there is a, so let's stop and take stock. Pivot position in every row tells you that no matter what B is, you have at least one solution. If you had a pivot position in every column, which we couldn't possibly here because you have more columns than you have rows, but if you had a pivot position in every column, that would tell you that there is at most one solution for every B. So pivot position in every row, which we can have here, and we do. We already know where the pivot positions are. We have a pivot position there, pivot position there, pivot position there, because we already did the row reduction for the homogeneous case. Pivot position in every row tells you that there's at least one solution no matter what B is. Pivot position in every column, which couldn't possibly happen here because we have at most 3 pivot positions and there are 4 columns. Pivot position in every column tells you that there's at most one solution for every B. So pivot position in every row, at least one solution for every B. Pivot position in every column, at most one solution for every B. You know you can't have a pivot position in every column this time because you have at most 3 pivot positions. You can't have more pivot positions than you have rows, and you can't have more pivot positions than you have columns. Okay. So let's see. What I'm going to do is row reduce again, but this time instead of having zeros to the right, I have the vector 2, 3, 2. Let's just save ourselves a little bit of time. Well, I guess I'm saving myself time by leaving this on the blackboard. But let's see how similar the row reduction is. You're basically going to do the same steps. So what did it say? 2, 3, 2. 1/2 times row 1 changes that to a 1. Row 2 minus row 1. Three minus 1 is 2. Row 3 minus row 1, 2 minus 1 is 1. Bet you wish that pause button was working right now. So you can see that nothing to the left of the line is changing. Row 3 plus row 2, 1 plus 2, that's 3. One-fifth of row 3, we still have the 1 and the 2 here. But 1/5 of 3 is 3/5. Row 1 minus row 3, that's 1 minus 3/5. It's 2/5. And again, if you don't like fractions, don't use them. You can use decimals. I'm perfectly happy with that. Don't let my personal prejudices influence you. I'm sure you have your own favorites. Row 2 minus 2 times row 3, so that's 10/5 minus 6/5 is 4/5. And we are just one step from the end, but I'm running out of space over here. Let me leave that on the blackboard and come over here and do the last step of my row reduction. Which is going to be row 1 minus 2 times row 2, the same as it was last time. So row 1 minus 2 times row 2, that makes a 1 there still. It makes a 0 here, which was the point. I still have a 0 there. And so row 1 minus 2 times row 2, that's 2/5 plus 8/5. Minus 2/5 plus 8/5 is 6/5. And row 1 minus 2 times row 2 is what I said. So 2/5 minus 8/5 is minus 6/5, I guess. And the other rows are the same. 0, 1, 0 minus 4/5. 4/5. And 0, 0, 1, 7/5. 3/5. And let's do what we did last time. We have x1 plus 6/5 x4 equals minus 6/5. We just don't have zeros over here anymore. And we have x2 minus 4/5 x4 equals 4/5. We have x3 plus 7/5 x4 equals 3/5. And we have x4 is free. And if we write this as a vector, sorry, if we write this like this, if we let x4 equal r, we end up with, let me move these numbers over first. So x1 equals -6/5, x4 -6/5, and x2 equals 4/5, x4 plus 4/5, and x3 equals -7/5, x4 plus 3/5, and of course x4 is 3. So writing this as a vector, we end up with, let's let x4 be r. So x1 equals -6/5, r -6/5, x2 equals 4/5, r plus 4/5, x3 equals -7/5, r plus 3/5, and x4 equals r. Get rid of this stuff now. So that means as a vector, x1, x2, x3, x4 equals -6/5 r -6/5, 4/5 r plus 4/5, -7/5 r plus 3/5, and r. Let's try to simplify that the way we simplified it last time. I'm going to do this in 2 steps. First, I'm going to break it into the part with r's and the part without r's. Part with r's is -6/5 r, 4/5 r, -7/5 r, r. In other words, identical to what I had last time. And then I have the part without r, plus -6/5, 4/5, 3/5, 0. Those both have to have 4 entries because I'm adding. You can't add 2 vectors of different sizes. And now I'm going to pull the r out. -6/5, 4/5, -7/5, 1 with r in front, plus -6/5, 4/5, 3/5, 0. So that's my x1, x2, x3, x4. x1, x2, x3, x4. Good so far? Okay, so for our original system, when we had zeros on the right-hand side, we just had r times this vector, all multiples of this vector. And we saw that that was just a line in R4, a line in four-dimensional space through the origin. Through, because this certainly goes through the origin. If r equals 0, then I have 0 times this vector. 0 times who cares is 0. It's the 0 vector. It also goes through the vector -6/5 or -7/5, 1. It also goes through twice that, or 3 times that, or 5 times that, or -2 times that. It's just a line through the origin. What's this? This is just a line that goes through the point 0, 0, 0, 0. What's that?
It's a line that goes through the point 2, 3, 2.
Yeah, it's another line that goes through this point. If r is equal to 0, then I have 0 plus this. So it definitely goes through that. -6/5, like x1 equals -6/5, x2 equals 4/5, x3 equals 3/5, and x4 equals 0 is definitely a solution. But so is this plus 1 of these. So is this plus 2 of these. So is this -5 of these. This is another line. It has one parameter, that's a straight line. So if we have one parameter, it's a straight line. It goes through this point, -6/5, 4/5, 3/5, 0. And it's parallel to this vector. So in other words, these two are both lines. These are parallel lines. Those are parallel lines. This one goes through the origin. This one, So I had one free variable, I have one parameter. I just used r. If I had two free variables, I'd have two parameters. I have like r and s. If I had two free variables, two parameters, it wouldn't be a line. What would it be? What's the two-dimensional flat version of a line? It's a plane, right? If I had two free variables, my solution would be a plane. The plane for the homogeneous would always go through the origin. If the thing on the right-hand side, if b wasn't equal to 0, I'd have another plane parallel to that. If I had three free variables, I'd have, well, I don't know. We don't have a word for this in English for a three-dimensional flat thing. In mathematics, you could call it a hyperplane. I'd have a hyperplane going through R4. This three-dimensional flat thing going through R4, in this case R4, because I have four variables altogether, because my original matrix A had 4 columns. That's why we're in R4. Yeah, so that's if that makes sense to you, that's great. How are we feeling? I'm gonna go over here so I can see your faces and your thumbs. Thumbs up, awesome, great. If this is making sense to you, that's terrific. Because this is really new stuff. This doesn't look like calculus. This is a new way of thinking. So if this is making sense to you, that's really, really good. So we've already talked about what it means for a set of vectors to span. We know that the vectors in the original matrix here, since we had a pivot position in every single row, we had a pivot position here, a pivot position here, a pivot position here, even though we couldn't see them right away. Once we row reduced, we saw that we had pivot positions in every single row. We know that this vector in R3, that's the vector 2 in the x direction, 1 in the y direction, and 1 in the z direction, and this vector, and this vector, and this vector collectively span all of R3. If you take linear combinations of these 4 vectors, in fact, you don't even need that one, you can get to any you can get to any vector in R3. I want to talk about the sort of flip side of that coin, but I see I have only 1 minute and there's no point in introducing the next topic, which is something called linear independence. So we'll have to save that. I know that I'm ending on a cliffhanger here. I hope you can wait until Friday's class to find out what's going on. If you can't bring yourself to wait till Friday's class, then go ahead and you can read section 1.7, and that'll give you a leg up on Friday's class. Any questions?
Do you have an idea of when the next homework assignment's gonna be?
Yeah, I think I'm gonna post the next homework assignment today or tomorrow.
Okay, thank you.
Sure. Bye, everyone.